Faraday's law was, again, discovered by accident, and it is a very important law because it bridges the connection between electric and magnetic fields on a very deep level. But let me talk a moment about what the law is and what it causes. So initially it was discovered that if one was to take a magnet and shake that magnet around a loop of wire, a current would flow in that wire. So for instance, if I take a bar magnet and I move it around a solenoid, as I shake it around back and forth, it was found that there was a current that began to flow in that loop of wire. And the same thing actually happened for an electromagnet as well. If I brought an electromagnet near a loop of wire, it would induce a current in that loop of wire. So when we talk about Faraday's law, we're really talking about the principle of induction. And the principle of induction works in many different ways, but it's summarized in terms of Faraday's law. And let's talk about Faraday's law. This is its expression mathematically, but we'll talk about what it means physically here as well. So first of all, I would say that when I talk about this epsilon on the left-hand side of the equation, I'm talking about an EMF, or an electromotive force. This is an EMF, which we mean an electromotive force. An electromotive force is just that. It's an electric force which causes motion of typically electrons, if I have a wire. It causes a motive force, and the motive force is caused by electrical influences. So EMF is, sometimes we use the word voltage or electric potential difference when there is this electromotive force present, or voltage or electric potential difference. It drives the flow of charge. So EMF, mathematically, we can write it as the integral of E dot dl that mathematically is the change in voltage, but it's a little bit different than ordinary voltage, which is caused by a chemical potential. This one is caused by a changing magnetic flux. And typically for an electric field that is caused by charges, the electric field around a closed loop, electric field lines don't form closed loop, but when we're dealing with EMF, in fact it does. So there's a non-zero change in electric potential as I go around a loop, which basically means electric field lines can circulate, meaning that I have electric field lines that have no source charges. But it turns out that these fields are in fact the same fields that we were dealing with when we talked about electric fields created by static charges, or the separation of charges, which is what a battery does. All right. And it has the exact same effect in what it does, although there's no actual battery that is setting up this voltage. You can think of this as a voltage around a closed loop. Now, in one sense, this does seem to violate Kirchhoff's loop rule, which says the total change in voltage around a loop is equal to 0. That's true when the electric field sources are charges. But here, the electric field source of the electric field is not a charge. It's a changing magnetic field. So you can have this voltage present, or this EMF present, even when there are no source charges. So what creates this EMF? Well, again, what does the EMF do? It makes charges move. If I have a conductor where this EMF is present, it would create a current. So Faraday's law says you're going to have an induced EMF. This is an induced EMF, which thereby produces an induced current. And you can think of induced current as this EMF that we're dealing with right here. It is equal to I times R. So if I have a wire present where the induced EMF is, there's going to be a current that flows, and that's the induced current. And that's strictly due to a changing magnetic flux. So this phi sub m term is magnetic flux. And we use the symbol B to designate magnetic field, so magnetic flux. And the units of magnetic flux are the Weber. And 1 Weber is equal to 1 Tesla per meter squared. So to remind you what magnetic flux is, magnetic flux mathematically is simply the degree to which the magnetic field lines penetrate through a surface. So it's the surface integral of B dot dA. This is a surface integral. Right? Imagine, for instance, this sheet of paper right here. If I have a magnetic field which is upwards, all over the page, there's going to be a flux, or a degree to which the field lines, in a sense, flow or penetrate through the surface of this paper. All right, and then finally, I want to talk about this negative sign, which is buried into Faraday's law, and this, sometimes we can refer to this as Lenz's law, which tells us the direction, ultimately the direction of the induced EMF, and thereby the direction of the induced current. So, for example, it basically tells us that there's something opposite happening when the flux, if the rate of change of flux is positive, this is the time derivative of the flux. If the rate of change of the magnetic flux is positive, then the EMF induced is negative. All right, let's look at an example of this, which will make it a little bit more clear. Let's say I have a bar magnet, and this bar magnet has a north pole and a south pole. Now we know that the magnetic field lines, due to a bar magnet, bar magnet would be an example of a physical dipole. The field lines circulate around. This is sort of an elongated, perfect dipole. The field lines are moving north to south outside the magnet, but inside the magnet, since this is due to the orientation of a bunch of spins, the field lines actually point south to north when you're inside the magnet itself. So all magnetic field lines form closed loops. There are no such thing as magnetic charges, which are the source of field lines, but it's due to moving charge, and charge can move in one of two ways. It can either drift, electrons can drift as in a current. A large number of drifting electrons will produce a magnetic field. But in the case of a permanent magnet, such as the one I have sketched, electrons can also, unpaired electrons in an electronic orbital they all have spin, and if I have an unpaired spin, and all those spins align as they do, for instance, in iron, or they can be caused to align in magnetic domains, then we can have a large macroscopic magnetic field. But we need a lot of electron spins to align in order to get a magnetic field. So magnetic field, again, caused by moving charge. Charge can move one of two ways. It can either spin or it can either drift along. And in the case of a permanent magnet, we have the alignment of a large number of electron spins, which produce the magnetic field. Okay, so this is just a magnet. This is my bar magnet. Now what if I have a loop of wire? Off to the right, right? Now that loop of wire is just a closed loop of wire. There's no battery or anything else connected to it. So, from what we know in the past, nothing should happen because there's nothing pushing on the charges in that wire to make them move. But what Faraday's law says, if I take this magnet right here and I move it to the right, that would change the magnetic flux through this loop. There would be more field lines pointing to the right through this loop. And since the magnetic flux is changing, it would induce an EMF. And since there's a wire here, we get an induced current that would flow. So to illustrate what this looks like here is if I move the magnet to the right, the magnetic field, the magnetic flux through the loop increases in this direction. Okay. Now we can think of Lenz's law as saying the EMF is induced so as to oppose the change in flux. This is a helpful way to, instead of trying to think about right-hand rules all the time here, we can think of Lenz's law as saying that the induced current opposes the change in flux. So if I have a magnetic flux which is increasing to the right, the loop of wire wants to decrease the flux through it. So the way it can decrease the flux is by generating its own magnetic field to the left. The way it can generate a field to the left is by causing a current to flow around the loop like this. Because then inside the loop, using the right-hand rule, taking my thumb in the direction of the current, the field inside the loop points to the left, and that kind of cancels the magnetic field out. So we'd have an induced current. The strength of it would be given by Faraday's law right here, just taking the magnitude. The direction would be given by Lenz's law, and we have to use the right-hand rule in association with the direction of the current flow. So again, so to repeat the argument again here, I move the magnet to the right. Magnetic flux increases in this direction. There's more and more field lines which start to penetrate through the loop to the right. The loop says, I want to decrease the amount of flux that's coming through the loop, so I'm going to create a magnetic field to the left. And the way I do that is by having a current which goes around in this direction, and that creates a magnetic field to the left inside the loop. All right, so this is a basic application of Faraday's law. There's many examples of the use of Faraday's law, such as transformers, electric motors, electric generators, any sort of hydroelectric dams, all involve turning magnetic fields, turning magnets inside a loop of wire induces a current, and we can convert, for instance, in the case of a hydroelectric plant or a coal-powered steam plant, we can take motive energy from the spinning turbine, and we can turn that into electric energy as the magnet is turned around and around inside a loop of wire.